Hi everyone, welcome to physics. Today we will begin with kinematics. Kinematics. Okay, so let's start with a word. What does kinematic word means? The term comes from the Greek word kinema, that means movement, that derives to kinein, meaning to move. It's the same etymology as cinema. It literally means motion, moving. Okay, so kinematics will be the study of motion. We will study how objects move without considering the forces that causes them to move. This study uses analytical geometry to describe the motion, regardless the mass, the shape, the mass distribution, color, etc. It considers the whole object as a particle. So a moving car will experience the same motion, can experience the same motion as a dot particle or as a boy that is moving. Okay, we won't care about the mass. We won't care about the shape. So in order to understand kinematics, we need some definitions. Displacement is the change in position. It's where was I versus where am I now. Velocity, the rate in respect with time at which position changes. How fast can I go? Can I get somewhere? Okay, and acceleration will be the rate at which velocity changes. So how fast can I go faster? Okay. Now, something that accelerates a lot can go slower than something that accelerates at a different rate. This means you can go from 0 to 100 in 3 seconds if you have a nice car, or you can go from 0 to 100 in 12 seconds if the motor is not big enough. Okay, that's the difference between acceleration and velocity. Now, how do we understand acceleration and velocity? Well, let's make an example. Picture a typical day going to school. Assume that it is 6 kilometers from your house. That's 6,000 meters in SI units, and it takes you 10 minutes, which is 600 seconds in SI units to get there. Well, by definition, the average velocity would be the distance traveled, the 6,000 meters divided by the 600 seconds. And we can say that you were moving at 10 meters per second. But we all know that it's not precisely like that, because there were some parts in the road in which you were going faster, like straight roads, or others in where you were moving slower, like traffic jams. So if we go a little more precise, instead of taking the whole 10-minute journey, we can take, I don't know, the straight interval, for example. Okay, so suppose that it was half a kilometer long and it took you only 25 seconds. Your average velocity then would be the 500 meters divided by the 25 seconds. And that's 20 meters per second, and it's quite different from 10 meters per second. And you get the idea. If you were passing someone, there were short periods of time in which you were going faster, or some others in which you were going slower. The thing is, if we do this interval smaller and smaller and smaller and smaller, we can get into the instantaneous velocity. Okay, we will be using the big four formulas. Okay, big four because they are four and it's everything we need. So hooray. And they will help us know the exact instantaneous parameters of objects that are moving. Instantaneous means that in that precise instant, what's going on. So these are the big fours. Okay, now let's analyze them. In order to understand them, first we need to know what each letter means. This triangle over here, the one that is on the side of the X, is called delta. Delta is always change. Okay, and we will define change always as final minus initial conditions. Okay, that's how much something has changed. So the change in X, which is displacement, the same as position, change in position, equals to 1/2 VO. Now let's look at this other symbol over here. This little zero over here is called a sub-index. Okay, every single sub-index that has a zero stands for initial. So we know that velocity is, we use V for velocity. So this would mean initial velocity, initial position, okay? Now, let's move on. T stands for time, okay? Now, if we go and analyze big four number one, this will tell us how much have you traveled, the change in position. If you know the initial velocity and the final velocity and the time it took to get there, okay? Big four number two will tell us the velocity at a certain specific time. Big four number three will tell us the position. Check how this is changing position or changing displacement, and this X is simply displacement, okay? So big four number three will tell us the position of a particle at the exact time. Finally, big four number four relates velocity with acceleration and change in position. Look, final X minus initial X. This is also called delta X, change in position. Now, in order to solve the problems, we need to understand some keywords. Resting, starting from rest, dropped, means that it was not moving and now it is moving. Okay, when you drop something in your hand, it's not moving. Once you let it go, it begins to move. When you are resting, you are not moving. That means that your initial velocity is always 0 meters per second. So from now on, every single time you read resting, starting from rest or dropped, the value, the numerical value for VO is 0. Slowing down, hit the brakes, or stopped. These are other three clues that will tell you something around the answer, and that something is that the acceleration is negative. Okay, so we defined acceleration as change in velocity. Change in velocity is final minus initial velocity. So if something is slowing down, the initial velocity should be bigger than the final velocity. So if you do that subtraction, final minus initial, we will have a negative number. That's why A is negative. Now, acceleration due to gravity is G. It has its own special fancy letter, which is G, that stands for gravity. Okay, now this doesn't mean gravity. This means acceleration due to gravity, which is always 9.81 meters per second squared. We will round it up to 10 meters per second square on quizzes, so the calculations are not that hard. So some strategies to solve the exercises. First, draw a sketch. The sketch will help you know what's going on. Okay, it will help you define whether it's going up, down, left, and right. Determine the components, okay, whether they're positive or negative. Remember, on X, the horizontal axis, to the left is negative, to the right is positive. On the Y-axis, upwards is positive, downwards is negative. Remember, we always convert from polar to rectangular. So if we do not have the components, the very first step you should be looking for is to get the components of the vector. Choose a suitable frame of reference and coordinate system. This will be more clear and more specific on the examples. But whenever you're starting, you have to define the starting position. And the starting position should be your 0, 0, the origin, the frame of reference. Then ask yourself questions about implications of changing motion, like what would happen if something stops, or if it slows down, or if I drop it. And finally, remember that trajectories are expressed in terms of position variables only, okay? So it will only tell us where is the object now. Example one, let's do one. A car can accelerate from 0 to 100 kilometers per hour in 3.2 seconds. What is its acceleration and how much distance will it travel at that time? Okay, so we have to focus on the big four because we're talking about kinematics, and kinematics is always with a big four. And the very first step, the 0th step, should be convert from kilometers per hour to meters per second. Once you have it in SI units, we have another video in which I explain how to convert. We write what we have and what we don't have. We have the initial velocity because it says that it can accelerate from 0 to 100. So from means that this is the initial velocity. We have the final velocity, which is 100 kilometers per hour in SI units, 27.77. And finally, the time, which is 3.2 seconds. Now, you should write down what you're being asked for. It's asking you for the acceleration, which is an A, and the distance traveled, which is the X. Now, we begin with our frame of reference. XY, our frame of reference, a coordinate plane. Then the particle, this is the dot. The dot can be a car, a person, anything can be it. So this will be the particle that is moving, in this case, the car. We know that it starts at 0 meters per second, so that's why I wrote VO there. And then at the end of the arrow, we get that the final velocity is 27.77. The time it took is 3.2, and we're looking for A and X. Okay, so now we have our sketch, and now we know what we're looking for, what we have. Okay, now, so where do we start? Well, we have already started with a lot, the sketch and the charts of what we have and what we don't. Now, how to pick a formula? We have to look for a formula that has everything that we have and only one missing variable. And the missing variable should be what we're looking for. Okay, so here are the big fours. Let's see. Let's see number one. Number one, we're looking for acceleration right now. So it should have everything we have and what we're looking for. If we're looking for acceleration, look that formula number one doesn't have A, so it won't work. Okay, we need to find another one. Let's see, formula number two. Number two, we have final velocity, which we do have, initial velocity that we also have, acceleration, that is what we're looking for, and the time, that is something that we have. So look, when you find this scenario in which you have all ticks, okay, and one question mark, this means you have all the information except for one thing. That's the one you can use. For the sake of the example, let's focus on number three. If we wanted to use big for number three, well, we have initial velocity, we have time too. We're looking for, here it is. We're looking for acceleration, but look, we do not have the position because we're also looking for it. So because we're looking for both of them and we have two in one equation, we can't use formula number three. So let's move on with number two. We can substitute the values and solve for A. It's pretty simple. You'll pass VO to the left subtracting, then the T dividing, and we will have this. Then you can substitute the values. Final velocity was 27.77, initial velocity was 0, 3.2 is the time, and then you just put everything on the calculator and pop, we are done. 8.68 meters per square second. We need to do the second question. The second question is asking us for the distance. Now that we have the acceleration, we can use before number three. Because we're looking for the distance, we know that the initial position is 0 because that's what we stated. That's why our frame of reference should always begin with a 0,0 in the initial position. So it is 0. Okay. We have the initial velocity. We have the time. Now we have the acceleration. We got it from the previous exercise. And we have the time. So again, we have everything except one, the thing that we're looking for. So we have the formula and we can substitute the values. This will turn out to be 0. VO is 0 times 3.2 will be 0. This 2 becomes a 0. This turns to 0. This turns to 0. Okay, and then we just have to do this operation. 1/2, 8.68 times 3.2 squared, and we get the 44.44 meters. Okay, so far, so good. It's easy. It's just a matter of looking for the correct formula. Let's do something else. This one was moving on the horizontal plane. What happens when something is falling? Okay, let's do example 2. You drop a 10 kilogram object and a 0.1 kilogram object at the same time. If they're at a height of 1.2 meters, how much time will it take to hit the ground? If you can see the big four, regardless of the mass, is the acceleration constant, okay? So when we talk about vertical dimension, the acceleration will always be g, acceleration due to gravity, 9.81. And it is always negative because remember that acceleration is a vector. And if it's moving down, the vector should be and will be negative, okay? Velocity and acceleration will be positive when the object is moving up and negative when the object is moving down, okay? Velocity at the highest point is always zero because it's going, it's a positive number until it reaches zero, and then it's a negative number because now it's going down. So the highest position is always when the velocity is zero, is the change in sign from positive to negative. This is our sketch, okay? Doesn't really matter. The most important part is for us to know where the floor is, where the ground is, okay? And where the object is at the beginning. Now look, I'm doing the frame of reference at the initial position of the object, okay? So this is our 0, 0. It's really important that you always do it in the same place. I mean, as a rule of thumb, it should always be the initial position of the object, okay? So it's better if the object is here at the beginning, put there the frame of reference, not here. I know that intuition sometimes might tell you, well, it's better if we put it down in the lowest position. Not for this class. For this class, it's better if you always put it at the initial position of the object. Okay, so at the highest position, we know that our height, y, is 0, and our initial velocity is 0. Why? Because it says you drop. And remember, drop is a clue word that will tell us, a keyword, sorry, that will tell us that the initial velocity is 0. Then, if this position, y is 0, the bottom position, the lowest position, will be when y is minus 1.2. Because you started here and then you moved downwards 1.2 meters. Okay, so once we have our sketch and we have our frame of reference, we can begin with the chart. The chart will tell us what we have and what we don't have. Okay, we have the initial velocity 0. We have the acceleration minus 9.81 because it is moving because of gravity. Okay, remember that this value is the same regardless the mass of the object. And then we also know that the position on y, the height, is minus 1.2, 1.2 below the original position. Okay, then the unknowns. The unknowns, we have the time, that it is something that is being asked, and the velocity that is not asked. So we will only focus on some formula that has time. Okay, we can use big for number 3. Why? Because it's the only one that has initial velocity, acceleration, final and initial positions, and the time. Okay, it do not have v, so we can use that one. Okay, this is the formula. X equals to xo equals vot plus 1/2 at squared. Okay, we can change these x's, which are positions, for y's because we're talking about vertical positions. Okay, and we will look for t. Now, important observation. If you can see, this has 2 t's. One t that doesn't have any exponent, which means it is an exponent of 1, and a t squared. Okay, this is called a quadratic equation. Big for number 3 will always be a quadratic equation. Now, if you're looking for the value of the variable that is to the square, that is t, we need to rearrange the formula and we need to do a lot of things. So let's start. Just keep in mind that this is always for BF number 3. The form of every single quadratic equation is this. This is called form in mathematics. Ax squared plus bx plus c. You can read it as something that is multiplying a quadratic term plus something that is multiplying the term that is not quadratic plus something that is just there equals 0. Okay, in this case we have, if we substitute the values, we know that y, the final position, is minus 1.2. We know that the initial position is 0 because we made our frame of reference like that. We know that our initial time is 0 because that's when you drop it. Okay, and we're looking for this 1/2 minus 9.81 t squared. Okay, now the final position is negative, as we said, because it is below the frame of reference. Now, we can simplify this and rearrange it. How am I going to rearrange it? The quadratic term, which is everything that is multiplying here, should be the very first thing we have, because that's A. The thing that is not multiplying anything will be B, and then this, that is a common term, well, should be reduced into C. Now, if you multiply 1/2 times minus 9.31, you'll get minus 4.905. So minus 4.905 t squared plus 0t, why 0t? Well, because the initial time was zero, sorry, the initial velocity was 0, okay, plus 1.2. Look that everything has to be on the same side. That means that we have to move this to the other side. That's why it turns positive, because all the terms should be on the same side and it should be equal 0. So, as I said previously, the term that is multiplying, sorry, the coefficient that is multiplying the quadratic term is minus 4.905. B is the thing that is multiplying the linear. B is what's multiplying the linear term, which is 0 in this case, and C is what's not multiplying anything, positive 1.2. Now we have them arranged. Now we are ready to finish solving this quadratic equation. Now, as you may or may not remember, the way we solve quadratic equation is with the general formula. Okay, so the general formula is x equals to minus b plus minus b squared minus 4ac divided by 2a. Our unknown is t, so this will be t, and we will put inside this formula the values of a, b, and c. Okay, look, b was 0, so 0, plus minus the square root of b squared, which is 0 again, minus 4ac, 4 times a times c, divided by 2 times a, 2 times 1.2. You put that in the calculator and it will tell you two numbers, two values. We always keep the positive number because we're talking about time. So this means that it will take 0.4946 seconds. If we round up, well, we can say that it's 0.5. Okay. Also, if you have the gray calculator, the Casio FX991, you can click mode 5.3. Mode 5 tells you that you are using the equation mode. If you see the number 5, once you click mode, it will say EQN of equation, or if it's in Spanish, EQUAC of ecuación. Okay, so you click on number 5 of equations, and then you have a couple of them. Look at number 3. Number 3 has exactly the form that I told you. AX squared plus BX plus C equals 0. We can write the corresponding values, okay? Once the equal key will be like the intro, so you will type mode 5.3, then minus 4.905 equals 0 equal 1.2 equal. Then you click equal, that everything is ready, and you click equal once again, and the calculator will give you x1 and then x2. You can see it's exactly the same number, it's exactly the same value. This means that regardless the mass, all objects fall at the same rate. And that's Newton's apple story. He realized that because some apple fell in front of him when he was thinking. Well, that's the story. So any object will reach the ground in 0.5 seconds approx if you drop it from 1.2 meters, every single object. An ant, an elephant, everything. Okay, now if we ignore the shape and the mass distribution and a lot of things, air resistance, for example. Okay, now what happens when we put vertical and horizontal things together? We get something called projectile motion. Motion because of kinematics, projectile because it's something that you are throwing. So if you kick a ball, a soccer ball, well, it will go up and it will go down just as if you throw something, okay? Just as if you shoot something with a gun or something like that. That's why it is called projectile. So in projectile motion, we have both things together. Horizontal, which will have some special equations, and vertical. These are simply the big four, just rearranged in a way that it's a little more clear. X for horizontal stuff, Y for horizontal stuff. And remember that the X and the Y axis are perpendicular to each other. So it won't affect others' magnitudes. It only affects its directions. So let's do an example. A ball is thrown at an angle of 30 degrees with the horizontal at 1.5 meters per second. Find the time required for maximum height, the time it takes until it hits the ground, the maximum horizontal distance, the times when the object is half at the maximum height, and the velocities at those times. Now, well, we start with the same thing, a sketch, okay? The sketch should always look like this. It's a curve named parabola, it's a parabola, okay, with the arrow of the initial velocity. The trajectory will only depend on the initial velocity of the object, okay? Now remember that it is a vector, so we need magnitude and direction. Now this black arrow represents the vector, and we need to get the rectangular forms, obviously, because, well, from polar to rectangular every single time. That's the zeroth, well, one of the zeroth steps. So we convert, we get Vox, look, the sub-index X representing that it's the X component with a cosine of 30, and Voy with a sine of 30. We get 1.3 and 0.75. Now we have velocity on the horizontal and velocity on the vertical. We need to pay attention to this slide because it will tell us what formulas to use when we're talking about horizontal and when we are talking about the vertical. So we have horizontal and vertical stuff ready. So let's start labeling, okay? We have the sketch and let's label everything we know, okay? Now we know that Vox and Voy are over there, okay? We know that every single time at the maximum height, the velocity on Y, not the velocity on X, remember that they are independent. The velocity on Y is 0, okay? And it's always at the half of the trajectory, okay? So the half of the trajectory means that the total time elapsed for the complete motion would be half of it, okay? And also it will be half of the horizontal distance, okay? This will be at the half of the horizontal distance, okay? Now, we know that the acceleration on Y is g minus 9.81, and that the acceleration on X is 0 because there's nothing to stop it. If you kick a ball, it would move according to Newton's first law of motion. We will see that on the next topic. It will move forever until something stops it. What's that something that stops it? Well, another player, maybe the grass, maybe the air, but something will stop it in our world. Now, in physics, we assume that there's nothing to stop it. So the acceleration on X is 0, okay? The path is a parabola, so it's a symmetric. This means what happens on the left side will be exactly the same as what happens on the right side. At the bottom, we have that T will be the total time of the projectile motion, okay? We will have the maximum displacement on X, okay? Because we won't count the bouncings or whatever happens next. And the height, the position, well, it's on the ground. So the height turns out to be 0. I'm using these two colors so we can differentiate the points. Okay, so let's start with example A, B, C, and D. At Y max, at the maximum position, we know that the velocity on Y is 0, okay? So we're looking for the time for maximum position. The velocity on Y is 0. We have velocity on Y, we have initial velocity on Y, we got it from the rectangular form. We have G to be the acceleration and we have T. We can solve for T and we would have Vy minus Voy divided by G. What I did is I passed this Voy subtracting to the left and then dividing everything. And then just simply substitute values. 0 for the velocity on Y, minus 0.75 for the initial velocity on y, okay, and minus 9.31, and it gives us 0.07 seconds. Now, we also know that the maximum position, let's get it. We now have the time. So we're getting the time with, we're getting the position, the maximum height. That's what is being asked on example B, on question B, I meant. And well, you just substitute the values. Y0, the frame of reference is always 0, 0, so the initial position will be 0. The initial velocity on y, we got it from the rectangular representation of the initial velocity vector. The time is t, 0.07 is this 0.07. Okay, and then acceleration due to gravity, minus 9.81. And again, the time, 0.07 squared. So the height would be, at the maximum height would be 0.02 meters. Okay, now, because the path is symmetric, well, if it takes the half to get to the top, it will take double that time to get to the bottom. So it's just, the total time will be double as the time for the half part. And then to get the horizontal distance, we use the unaccelerated formulas, okay, which are for x. Delta x equals to VOXT. VOX is 1.3. We got it from the cosine of the angle, the rectangular representation of the initial velocity, times the time. The time, well, the complete time, because remember that this formula tells us the position at a certain time. So if we're talking at the end, well, we use the time for the end. And it would move 0.18 meters on the x-axis. Look, I'm using y with y and x with x. I never ever, for no reason, I never use y things on the horizontal things and vice versa. It's horizontal in x, only in x, vertical on y, only on y. Now we can do example 3, letter E. The problem is asking us for the time at a certain height, half the maximum height. Okay, so the height is on the y-axis, so we will be using y-axis again. Let's see. We know that the position is half the max. So I will put half the max on y. Y0 is 0 because the initial position is always 0. And then, well, the initial velocities, and we will be looking for the t. Okay, so y max is the, we're looking for half the max. So 0.02 divided by 2, 0.01. And then in order to solve, I will substitute the values. I have 0.01 here, 0 to be this. VOY, it's the same VOY, 0.75, and 1/2 GT squared. And as previous example, we have a quadratic equation. Okay, you can solve for t and we'll get 0.13 and 0.01. Now, these two t's, you got it from, if you check slide 13, it explains how to solve quadratic equations. You can use the calculator or you can use the general formula. These two times, port 13 and 0.01, let's go back a little to see the sketch. This is the sketch. When the object can be at half the maximum height, I don't know, somewhere around here. Oops. It can be at half the maximum height, something around here, but also on the other side because it is symmetric. That's why it is giving us two times, because at the beginning it is here and when it is falling, it is here. And those two positions happen to have the same height. Okay, these two positions. So the answers are both. Okay, let's get back to this. Okay, so the answers would be after 0.13 seconds, it will be at 0.01 meters, and after 0.01 seconds, it will be at 0.01 meters of height. Now, finally, letter F, we need to report velocities as polar vectors. Now let's get a little back. So velocities are vectors. We're talking about the velocity when the object is at half the maximum position. So it can be over here. Let me put it a little bigger. So it can be over here and it can be over here. Okay, well, assuming that they are both at the same height. They're kind of like at the same height now. Good. Okay, now, if we watch the components, Well, this component has a positive y and a positive x, while this component has a positive x and a negative y, because now it's moving down, not up. Okay, so for this, we will get the x component and the y component of both cases, and then we will convert it into polar vectors. Okay, so let's get back to it. So the velocity on x is constant, regardless the time, regardless the position, it will be 1.3 meters per second. So because y is accelerated because of gravity, we need to get Vy at both times. So this is what I was explaining you on the previous drawing. I'm looking for Vy at this position and Vy at this position. This position has a time of 0.01 and this position has a time of 0.013. With the big 4 number 2, we can get Vy. Vy is just the initial velocity times g, always negative, times the time. And we get the time, the velocity, sorry, at time 0.13. So the rectangular velocity would be 1.3 comma minus 0.052. We can convert to polar and we get the polar velocity vector. And then for 0.01, we do exactly the same thing. We substitute the values and we convert to polar. Well, thank you for watching kinematics lesson, kinematics lecture number 1. Remember that we have all the face-to-face classes to solve questions and exercises. Until next lecture, have a nice day.